So the topic is mitigating position bias in hotels recommender systems. My name is Yinxiao. I'm a software engineer from Meta Platforms, and this work was performed while I was at Tripadvisor. Nowadays, recommender systems rely on a lot of recommender systems rely on a lot of data to train machine learning models to rank results for a given query, and implicit user feedback data have become the dominant source of data collection due to its abundance and the low cost, especially for major internet companies. However, one key challenge of using implicit user feedback data is its inherent bias. Typically, there are 4 types of biases from implicit user feedback data: position bias, presentation bias, exposure bias, and the quality of context bias. Position bias is that users are biased towards clicking on higher ranked results. Presentation bias is users tend to click on results with seemingly more attractive summaries. Exposure bias is that users can only be exposed to a part of the items. Quality of context bias is that users' click decisions are influenced by the overall quality of the results in the list. Among the 4 biases, the position bias has the strongest effect on users' click. So in this work, we will focus on debiasing the position bias in order to fully leverage the power of implicit user feedback data. Again, position bias is that users are biased towards clicking on higher ranked results. There are several explanations for that. One explanation is that users may not have evaluated the whole list before making a click. One example is a cascade model, which assumes that users sequentially view the results from top to bottom, and they will click on the first relevant result as they are scrolling down and stop. However, it has been argued that this cascade model is biased and will lead to a ranking model that tend to reverse the existing order. A second explanation is that the results on the top are generally more relevant than results on the bottom. But since each hotel impression along the list has a different propensity of being observed, this should be considered for position bias mitigation. So in this work, we propose to incorporate these 2 existing explanations to build an unbiased training data set for recommender systems in Tripadvisor Hotels. Consider a simplified example of implicit user feedback where there are 5 hotel impressions in the list, and the user makes a click on hotel number 3. Since the user clicks on hotel 3 has been evaluated, and according to the cascade model, we assume hotel 1 and hotel 2 are also evaluated, while hotel 4 and hotel 5 are in an unknown state of being evaluated or not. To build an unbiased training data set, we will sample the hotel impressions, and the sampling rate of each hotel impression should be equal to its propensity of being observed. Specifically, to construct the training data set, our approach first discards all the search logs where no click or booking happened. And for the remaining searches, we divide the list based on the lowest hotel position that was clicked by the user. The hotel impressions on or above that position will be kept in the training data set without sampling, while hotel impressions below that will be sampled based on their estimated propensities, which we will discuss on the next slide. Then the hotel impressions that remain will be used to create training pairs for model training. It's also worth mentioning that since this approach mitigates the position bias via debiasing the training data set, it does not require any change on the model training or serving infrastructure or impact the complexity of the model. For propensity estimation, we assume that users have evaluated all the results on or above the last clicked position. For hotels below that, their propensities will be estimated by extending the classical position bias model. According to the position bias model, the probability of evaluating a given result is equal to the probability of a click on that result divided by the probability that this result is relevant. For hotel relevance estimation, we have found out that for online travel agencies, the number of bookings is a very strong signal of hotel relevance and is aligned with our final business goal. So we will use the mean of historical bookings at position K to describe the average hotel relevance at position K. So with this approach, we can calculate the propensities at different positions. In this slide, we will show both the measured click curve and the calculated propensity curve. Both curves are normalized. The click curve on the top confirms that users are highly biased towards clicking on higher ranked hotels, and since the click curve is steeper than the calculated propensity curve, it indicates that in general, we're already promoting more relevant hotels to the top of the list. To evaluate the effectiveness of propensity sampling, we ran 3 online experiments in Tripadvisor Hotels' best value sort for 2 weeks and evaluated the performance by the number of clicks. 3 different variants on how to sample results below the lowest clicked hotel will be tested. Specifically, we have chosen the 100% sampling strategy as a control, where all the hotel impressions of a query with at least 1 click are kept in the training data set. In test 1, we use a sampling rate of 80%. In test 2, we apply propensity sampling to hotel impressions. It's noted that for all 3 experiments, the model architecture is exactly the same. Since we use all the raw search logs from the past 28 days to construct the training pairs, the amount of data used to train the models in test 1 and test 2 is slightly lower than the control. Here are the experimental results. Among the 3 experiments, the model with propensity sampling has the best performance. Compared with the control model, it improves the clicks by 1.5%, which is statistically significant. This model also outperforms the model with a constant sampling rate of 80% by 1.7% in clicks. This result shows that our approach is effective at mitigating position bias as it has generated more user clicks and engagements in the online test environment. In conclusion, we proposed a simple and easily adoptable method that fully leverages user actions with propensity sampling. Online test experiments show that this method leads to significant performance improvements. Since this approach mitigates the position bias by debiasing the training data set, it does not require large investments in infrastructures to support more complex models. That's it. Questions?